there will be, of course, the stars. And immediately the question, how many stars in the night sky? Have you ever tried to answer this question? How many stars in the night sky? Maybe someone will ask you in the future and you can share your knowledge. And you can always answer. All depends what are you asking about. If you are asking about the local sky, as every one of us can see with naked eye, we can say we are able to see about 3,000 of stars. Some tools like binocular, like telescope, they can be amateur telescopes or more professional telescopes. Everyone tool increases our view, and with some professional astronomical telescope, this number increases up to 10–15,000 of stars which we can see in our local sky. But the main question, how many stars in the sky means in the cosmic space, I always use some comparison. Let's please sit down and count how many grains of sand in the whole planet Earth. And that time you will exactly get the number, how many stars in the cosmic space. But coming back to our stars, when we see the night sky full of beautiful, fantastic stars, we should remember that this is something like we would observe some city, some town from the helicopter. When we will take the plane, the helicopter, and would fly above, we will see the city and some people, citizens of this city, and we will see whom? We will see babies, newborns, which they were just born, yes? We will see babies older than 1 month, because this is the border when we say newborns and babies. We will see people, children in daycare, in preschool. We will see children in elementary school. We will see youth in their high schools, colleges. Then we will see older people, even as old as I am. Then we will see people who already retired and people who are 100. I wish everybody minimum 100. And we will also see, unfortunately, this is sad, but we will also see people who are dying, yes? We cannot see people who already died, but just we see the symbols, if they are some cemeteries, but people who are dying. And this is the same. We can find just the common way, observing the sky and observing some city, that objects, the stars, seen by us in our night sky, they are very young. We can call them newborns. Babies, they are young stars, they are older stars, they are very old stars, and we also can see, this is the difference, we can see just stars which already died. How to find them, how to recognize them, I will tell you during this presentation today. And in our human life, we say just the age. Yes, we see people in different age. For stars, better works when we say we observe the stars in their different stages of their evolution. Yes, this is always the better word when talking about the stars, when we use just the stages of their evolution. But when we say the star's life is also correct. Nobody will complain, nobody will bother us when we will use the word star's life. Stars live, stars life. Okay, so this is like the general view, and I would like to go with you today very simple and very fast with no details like I always introduce when teaching astronomy, through the process called the stars formation. Because if we want to talk about supernova, we should know where are they from, means how did they form. The star which became as massive, as exploded must previously be formed. And this is why these few slides about the stars formation process. Maybe surprise, maybe not, but the stars usually are formed in the big clouds. Cloud, just the big cloud, like we can imagine the big cloud in the sky, and in the cosmic space, these big clouds, they are called molecular clouds, and look please, in extremely low temperature. This is what many times surprises people. Why extremely low temperature? Such we relate our knowledge about the stars to very high temperature, yes? If they must produce the energy, they must be so hot. And this is very true. I added here, this temperature just increases progressively during the process of formation. But initially, molecular clouds, they are very cold. The temperature there is like negative more than 400 Fahrenheit. I will not torture anybody by Kelvin scale, but this is very close to absolute zero of Kelvin scale. What in Fahrenheit means more than negative 400 Fahrenheit. And then in this molecular cloud, there are many future stars, means many candidates. This is also something what distinguishes us, the people, from the stars. Our deliveries, they are simple like the most often one baby is born. Sometimes twins, sometimes 3 children at once, yes? But normally, when we say the statistics shows that statistically we are delivered as individual babies. For stars, it works different. They are formed as the big groups of future stars, the candidates for future stars, in huge and cold, in the very center, molecular clouds. What's the next? And the next, this huge molecular cloud is fragmented into the smaller pieces. Astronomers call them the clumps, and each one clump later becomes a nebula. So we can say the initially big molecular cloud, later on it means many nebulae. And each separated nebula, this is exactly the future star. In it, in the very center, the future star will form. Initially, it will be protostar, like a prototype of the future star. And after years, this is what also distinguishes and differs us and the stars, after not few months, but after many million of years, sometimes after billion of years, as the star formation process goes, the protostar becomes a real star. This clump, I just took the balloon. I think this is the best example as the big molecular cloud was fragmented into clumps. And then every clump became nebula, means it became more flat, yes? And it started to rotate. In the very center of this flat nebula, the protostar was formed. And the temperature and density gradually started to go up in the very center since when the rotation process. When I teach my students, I usually like the comparison here when I say, let's imagine please you are cooking the soup now, yes? You put all ingredients, only the pot has the shape. Here the shape is irregular, yes, not as perfect rounded, yeah? But when you stir your soup, you see that the most of ingredients there in the very center, yes? This is where our protostar is in, okay? So, our protostar was located in the very center, and after many other processes, just something when maybe you heard about infalling gas phenomenon, some other processes like T-Tauri phase, not all stars, they go through this waiting room, but some of them, yes. Finally, after millions of years, the initially massive star is formed in the very center of this molecular cloud. Why I highlighted initially massive? Because it will be a very important parameter to understand later on, next few minutes, what means supernova. For astronomers, initial mass of star is a very important when we classify them. So this is why by red, initially massive star. And this initial mass of star depends how big was initial molecular cloud and later the clumps and the nebulae. More massive stars will be formed in the bigger molecule, in the bigger nebulae, less massive stars in the less massive nebulae. The star was born. The newly born star, like the baby, not the baby, the newborn. The baby will be after some time, yes? The newly born star is, say, in astronomy, when this object which was created based on protostar is able by itself to produce the energy. In the very center, in the core of every star, I have some example of star, but of course the model, yes? In the very center of every star is just the mystery, the miracle, I'm joking of course, the energy is produced thanks to what? Thanks to chemical fusion of hydrogen into helium. It means hydrogen is a fuel, helium is a product. And beside of helium, enormous amount of energy is released. Beside of helium, of course, some other side products, they are created, means the other chemical elements as we can find them in the periodic table of chemical elements. But this was just the secret. The moment as astronomers count the age of every star is the moment when the star was able to start its own production of the energy. Just small digression, maybe surprise, maybe not, but this, based on current astronomical knowledge, we know that when nebula, when the protostar, usually if any planets they are formed around, they are formed just at the edges of this, excuse me, nebula, if any planets are formed, they are formed earlier than this central object, protostar, is able to produce the energy before this central object became a star. So sometimes hundreds of millions of years is needed after the planets were formed, as finally the star was born, means was able to start to produce the energy. And what's the next? After the star was born, it takes its own place on some graph diagram which astronomers use to analyze the stars in the cosmic space. This is the Hertzsprung-Russell diagram. The history of this diagram is so interesting. Two astronomers, Russell in America and Hertzsprung, if I remember well, in Denmark, in Europe, they started their work independent. Absolutely, they didn't know one about another one. And they started to plot the stars based on their sizes and masses, on some kind of diagram using the axis, like horizontal axis with the temperature, and the vertical axis as luminosity. Both did identical work. Nobody knows why. They both used on a vertical axis luminosity in logarithmic scale. It probably worked mathematically better as they could fit all objects in the diagram. What is a little different of well-known for us coordinate system is that when we have typical 2D coordinate system in math, we have both axes, that y going up increases and x going to the right increases the numbers. Here on this Herschel-Russell diagram is a little bit different because, look please, analyzing x-axis, these values, these quantities which they are put here, means temperature of star, they increase but going to the left. Yes? It was also some mathematical trick if the diagram can be very well read. And a few words about this temperature. The temperature here is in Kelvin scale, but don't worry, I calculated everything in Fahrenheit, so I can show you the range. 3000 in Kelvin scale, what is official scale in science, is about, if I remember well, almost 4,000 in Fahrenheit scale. And we call them the coldest stars. What is interesting and simplify our astronomers' work, their surface is red. When we observe the sky and see the red objects, it's a big probability that this is the star with low surface temperature, about 3000 Kelvin, 5000 Fahrenheit, and, excuse me, I will check to make sure how many, yes, I said correctly, about 5 or 6,000 of Fahrenheit, because numbers, this is not my best side. And these, the coldest stars, and their surface is red. Then, going to the left, temperature, surface temperature of stars increases, goes up, and we observe the hottest stars in the sky as the blue stars. Their surface is blue. So the stars help a lot in our astronomical work because they present their surface temperature by their colors. Look please, our sun. Our sun is yellow star. And our sun is just medium in its surface temperature. By the way, our sun is very nice star, very helpful, because it's medium in everything what we would like to say about. It's medium in its mass, it's medium in temperature, medium in its age, just fantastic star, and we are so lucky that we have our sun as the main star in our solar system, thanks to what? We just exist. Yeah? So, the temperature and luminosity. What means the luminosity of the star? Luminosity of the star is just the energy which is produced, then transported to its surface from the core to the surface, and sent everywhere identically in every direction. No one direction is like preferred. Everyone has the same rights, yes? And this is what astronomers call the luminosity, and this is what is on the Herschel-Russell diagram on y-axis. Why logarithmic scale? Again, mathematical trick. It was easier to use to plot the stars. And what was found? And what was good? One, this is the luminosity as our sun has. Our sun became like a reference star with luminosity 1. Every star which sends more of of energy and light around itself than our sun, in this scale has this luminosity bigger than 10, and look please the exponent, 10, 10 to the second, 10 to the third. Every star in the cosmic space which sends less of light, less of energy around, is classified here below 1, such again our sun is medium and is classified as luminosity 1 on this diagram. And look please what happened. Both and Hertzsprung and Russell, they got an identical pattern, just that most of stars here, they are only representatives, of course, they were found by them like along with the line from top left to the bottom right. And astronomers later on, when Hertzsprung and Russell met during some conference and found what they did, astronomers immediately accepted their diagram and started to name the patterns as these two scientists got when plotting the stars. So this line got the name main sequence. And all stars which they were formed and already produced the energy, started to produce the energy and continue this energy creation, production, they are located on the main sequence. Now you can ask me why there they are different stars and here different. Again, look please on their temperature. Also, another very important criterion, mass. I highlighted before initial mass of star. The lowest massive stars, as after formation process are able to produce the energy, they are here. They must pass criterion that they are more massive than 8% of our solar mass. What is our solar mass? Do we remember from school? If I put in numbers, it is about 1.9 times 10 to exponents 30 kilograms. But I think everyone is familiar with the word mass, yes or not? Mass, the amount of components, yes, not weight, because they are two different things. Mass is measured in kilograms. Weight is a force, exactly gravity force, which based on mass, but is not straight a mass. And many people do the most common mistake when thinking about the mass, that bigger size means bigger mass. No, not always. Sometimes it works, but not always. Look please, 3 balls, yes? And when we would measure mass of each one, this one would be found with the lowest mass, this one with medium, and this one with the biggest one. All depends on density of material, on the properties of matter which created it. But, coming back, for stars, it works. If bigger mass, bigger size. Yeah? So the lowest massive stars, as they were created after formation process, they are called red dwarfs, and they are between 8% and 50% of solar mass. Here, going up, we have lower massive stars, medium massive stars, and more than medium, still less massive. Our sun is medium, rather less massive than more massive star, and is like in the middle of this main sequence. The most massive stars, which they have the biggest sizes, and immediately we can see they are the hottest, they are at the top left of the main sequence. The other patterns of the Hertzsprung-Russell diagram, they are supergiants, giants, and white dwarfs. Please see on them here and remember these names, because talking about supernova, we need to touch these magic words. And why the sun quickly because, again, we compare a lot in astronomy to our sun sizes, to our sun mass, like on Hertzsprung-Russell diagram. This is why, please become familiar, our sun will be like reference today, and many times when talking about supernovas, we will use solar masses. Means solar mass is one individual, 1.9 times 10 to the 30 kilograms. And Hertzsprung-Russell diagram is like here very simplified, and as I say, how long do the stars spend on the main sequence? As long time as the fuel in its core. When the fuel is used, means hydrogen in its core is used, the star prepares itself for dying process. Just one stage of evolution is done, and next stage of evolution starts. And then its gravitational equilibrium is disrupted. Look please, when observing the stars in our local sky, in deep cosmic space, the stars always look like spherical objects, yes? The secret is that they present some equilibrium. This energy produced in the very center and transported to the surface is balanced by huge gravity force, which is always attractive force. Every star is massive. Even the lowest massive stars, they are very massive. If bigger mass, stronger gravity force. So the star attracts everything to itself. And this force is balanced by the pressure as the energy from the center is transported to the surface. This is why stars keep their beautiful spherical shape. When the stars are dying, this shape is like disrupted. If the star is unshaped, it increases, it starts to behave like a bubble, yes? When we blow the bubbles, prepared from just the soap, yes? We see they are spherical but not stable. And this is the same what happens to the stars when they finish their life at the main sequence and they just move into the next stage of their evolution. How do they behave when leaving? Astronomers call it, they leave the main sequence. When they are leaving the main sequence of Hertzsprung-Russell diagram, initially the stars do, all stars, no matter, very massive, very low massive stars and very massive stars, they just do the same. They increase their luminosity, this is why we stopped with the word luminosity. They become brighter and they just move, like astronomers say on the diagram, they move to the right. And again, no matter the stars, no matter the mass, all stars do the same when leaving main sequence. What happened in their core? Fuel was used. The core became empty. And that time, stars, they are very smart, yes, they don't want to have empty core. Their core is filled out quickly. This used already hydrogen makes the shell, like the ring around empty core, and emptied core is filled out by next, the most common chemical element in the cosmic space, helium. And what's going on? The stars, some of them, the lowest massive, no, but a little bit more massive stars, they are able to burn this helium which filled out empty core. So now our star is so bright because this helium was able to be burned, is in fire, still hydrogen shell around where the hydrogen is still burned and the star like is still working. What happened to the lowest massive stars? They were not able to burn helium. They just finished their life as the blue dwarfs. Later they become white dwarfs, and many billions of years later they will become black dwarfs. But we are not interested about the lowest massive stars like this. We are interested about more massive stars and very massive stars, because here supernova may occur. More massive stars, medium massive stars, they were able to burn helium, and the process is repeated. After helium in their core was absolutely totally burned, the core became empty again. This emptied core was filled out by next chemical element, typically by carbon, sometimes the mixture carbon-oxygen. And now the star, medium massive star, it has two shells. It has like hydrogen initially, made shell, helium shell, and a lot of mixture carbon-oxygen in the very center. Medium massive stars, they stop this portion, this part, this stage of their evolution. Now, they become red giants, and later they collapse to become white dwarfs. But what about our candidates for our supernova? Look, please, for them, the process is repeated many times. The core is emptied, and next chemical element filled out the core. These stars, they are so massive, they are able to burn this next chemical element. And the result is that, look please, many shells were created for a long time, for as long time as finally iron. Iron will be the last chemical element which will fill out the empty core. No one star is able to burn iron. It's based on their smartness, because iron, burning iron, these reactions, they just needs the energy. They rather consume the energy. So not production of the energy will be observed, like should be for stars, only consumption of the energy. And this is why this is the end of end, even for very massive stars. When iron filled out the empty core, the star became supergiant, because look please, it still grew up, became so huge, and became a red supergiant. Increased its volume, its size, its mass many times. These stars, they are the best candidates to become supernova. And look please, which stars are we talking about? These which initially, after they were formed, they had the mass and they spent their life on main sequence of Herschel-Russell diagram, they had the mass between 8 and 50 solar masses. This time, their iron core is like not able to keep the mass which surrounds it. It initiates a quick collapse of this iron core. And this quick collapse of iron core just initiates the chain reaction. The next shells, they start to collapse, and finally these processes, they go fast in time. I will show you the time range, how does it go, but this huge collapse initiates the big explosion. And this is why we, the observers, observe a supernova, but be very careful, not like supernova with nothing else. We observe supernova type 2 or type 1b or type 1c. In this range, as initial masses of stars, they were after formation process, the types of supernovas can be observed. They are type 2, 1b or 1c. I explained here with details just fast-moving electrons initiate huge explosion. What means these fast-moving electrons? It just shows, look please, core collapse, this huge core collapse, which has the size like 5,000 miles across, yes? And the temperature enormously high collapses in the time less than 1 second, initiating the chain reaction that next shells, they start to collapse simply, still pretty fast. We see, oh wow, 1 day, no, fast. But 6 months, still okay, fast. When we, the people, see 600 of years, we say, oh, Jesus Christ, this is not quick. For stars, yes, this is very fast. When their formation process, they are millions of years. If some other processes in stars, it takes millions, sometimes billions of years. What means 600 of years? Yeah? So pretty fast collapse initiate this huge explosion. And something about statistics. What happens in typical galaxy, like our galaxy, I say typical. Our galaxy, by the way, is not as typical as we may think, because our galaxy is special. We live in, this is why this is special, and also our galaxy is one of the oldest galaxies in the cosmic space. Our Milky Way galaxy was formed only 1 billion of years after the universe was created, after Big Bang. So we are so happy and we should be proud where we live, yes, in one of the oldest, and by the way, not the biggest, but one of the bigger galaxies in the cosmic space. And what about typical galaxy? Usually astronomers say few explosions like supernova in typical galaxy per year. Here, when some other astronomers would be in the room, would be immediately the fight. 1, maybe few, maybe 12, maybe 15, yes? Because all depends what research does the astronomer do. Sometimes the conclusions, they are different. The problem is that not always we can see this fantastic, beautiful explosion which can make the cosmic space so bright, like shines entire galaxy, shines our sky, is beautiful, is fantastic, and is seen for many days. So if we are lucky, 1 time per 100 of years is the statistics we should see. But the problem is, this supernova type 2 explosion or type 1b, type 1c may occur in different places. And we will not be able, it will be to fill out statistics, but we will not be able to see it. And this is why we are not lucky, because we live only, I wish everybody 100, but only maybe 100 or a little bit more of years. And what do they leave behind? Typical explosion like supernova type 2, 1b or 1c, they leave behind or neutron star or black hole. Neutron star, when the star initially was less massive, and black hole when initially the star was more massive. And see please this, when the star initially was as massive as 140 solar masses, what also could happen in the cosmic space, this dies thanks to the explosion called supernova, or sometimes astronomers with details add supernova type 2P. There are some details of classification. What does it mean? This also, the core collapses, then enormous amount of energy makes a huge explosion, but these stars, they leave behind nothing. Just if we would like to imagine this unimaginable explosion, this is like when I would blow the balloon as much as it would explode, then we would not find any pieces of this balloon on the floor. Everything went back into the cosmic space. No leftovers. Not any neutron stars, not any black holes. And sorry, too fast. When very rarely, but it happens, initially when a star was as massive as 250 of solar masses, it may finish its life as hypernova. Also, enormous explosion, but it leaves behind supermassive black hole. And the special case, the last one, about supernovas, it may also happen for less massive and medium massive stars. I didn't lie you. I told you, typically, less massive, medium massive stars, like our sun, they finish their life by collapsion process. They collapse and they become white dwarfs. They only go through red giant phase. They never go through red supergiant. They are not able to burn oxygen or carbon in their core. But it may happen some special case. This is when this less massive star becoming white dwarf was initially in a binary system, means had a twin. Half of population of our stars in the cosmic space, they live in binary or more combined systems. What means two or more objects, they orbit the common center of mass. Yeah, means just the average in distance point which shows the average masses. When one star is very massive, one is very low massive, this common center of mass will be closer to this more massive object. So, if it happens and the less massive star becomes white dwarf but was in binary system, it may happen that this, during the creation process, white dwarf may start to still grab the matter from its companion. If its companion was bigger, this white dwarf can grab a lot. Yeah? So when it grabs a lot, it increases, its mass increases. And it may happen that its mass will increase up to 1.4 of solar mass. This specific border, 1.4 of solar mass in astronomy, is called Chandrasekhar Limit to honor the astronomer from India who got the Nobel Prize thanks to his work in astrophysics area in, if I remember, 1983, and Chandrasekhar. And it may happen that this potentially white dwarf became as massive as 1.4 of solar mass. Then this system is not able to keep its huge mass which was created before, and the whole system starts to collapse, initiating explosion. And this is the explosion which astronomers call Supernova 1A. Just special case of supernovas. Look, please, not core collapses. The whole system collapses and explodes, leaving behind nothing. Just like the very massive, about 100 solar masses, nothing. everything goes into the cosmic space. And the comparison, because classifications of supernova, they are as many as astronomers who, I'm joking a little, as astronomers who are working on it, but the truth is, it's hard to classify supernova. All depends what is our point of view. Our point of view today was mass of star. So we analyzed as massive stars can explode as supernova, less massive stars, they cannot. When they reach some mass, they can. But initial classification of supernovas, they didn't come from masses, original masses, initial masses of stars. They came from analysis of spectrum of this explosion. After explosion, astronomers analyzed the spectrum, and the first classification point was if hydrogen lines, they were in the spectrum or not. When hydrogen lines, they were in the spectrum, astronomers classified it as supernova type 2. When hydrogen was not observed in the spectrum, astronomers classified it as type 1. This is why it's complicated today, because when we see type 2, we say, hey, I understand 2A, 2B, 2C, but not 1B and 1C together with type 2. But it is, yes, in astronomy it is, but based on historical classification. 1A, rather silicon, but not hydrogen lines in the spectrum of light analyzed after that explosion. And the comparison of light, luminosity. Yes, look please. These white dwarf supernova type 1A, they are brighter. When they explode, they show the peak of luminosity, means the energy sent everywhere around bigger value than these massive stars like supernova type 2, 1B, 1C. And time in days, as I say, for many days, it makes the brightness in the sky when we are lucky and we can observe it. Anyway, just as I said, all depends, we base today on the mass of star, and I put together summarization. What happens? Red dwarfs? Absolutely not. Sun-like star, special case, supernova 1A may happen, but generally, for the stars which they were initially supergiants, blue supergiants or supergiants, supernova may happen. For a little less massive, up to 140 solar masses, it will be supernova type 2, 1B, 1C. More, it will be supernova with no extra name, or hypernova. Anyway, anytime when any explosion or the stars dies with no explosion, the most of material which was in its interior goes to the cosmic space. And this is something what is fantastic and shows as nice, as intelligent, as smart is the cosmic space. Reusing, recycling, this is the cosmic recycling. Stars, when dying, return their interior into the cosmic space. The cosmic space is waiting for it and reuses this material for next objects which they are still formed. So we do not have to be afraid. We can sleep well. It will be still a lot of material in the cosmic space to keep it alive and to produce the new stars, with beautiful supernovas as well. Thank you so much.
Well, thank you for coming today. Thank you for presenting.
I'm so sorry.
Oh, that's okay. Does anyone have any questions before?
What type was it? 1054 explosion, what type of supernova was it?
It was the most common, still astronomers find in this issue. Probably type 2, yeah, like the most common. But some astronomers found that that star was more massive and tried to classify it like 2P, type 2P. Still the discussion, as I'm saying, everything what we have, they are computers and math as a tool. We analyze, yes, because we do not have the object today as we can analyze. We only based on some research and descriptions which they were done before. Like if it happened yesterday, we would call to the chemists and say, hey, show me the analysis of spectrum, yeah? But this happened in 1054. People didn't have computers. People didn't know what means spectroscopy, how to analyze the lines, yes? So we think type 2, but if astronomers, I am not astrophysicist straight, but if astrophysicists announce next few years the different type, I will not be surprised.
Thank you again, and thank you for the next couple. One will be virtual, next lecture, and then the two after that will be on Zoom live with Lauren Taylor. Will talk about 1054 and specifically and native science in North America. We have someone who will be talking about the science and ancient Aztec world and their line of sight astronomy, and then the third person will talk about his work at Copan and the mines and their work in astronomy too in the variety belt. So join us please again, and thank you again.